G'day viewers. In this segment I'll complete our look at the Domain Name System or DNS. So in the first part of looking at the DNS we talked about the distributed namespace. In this part I'm going to focus on how we perform resolution and map host names to IP addresses. So just as a quick recollection, here's where we were. We talked about the distributed namespace or the hierarchical namespace, which you can see in front of you, and we talked about the use of zones or contiguous portions of the namespace as the way that we were going to separate it into pieces that we could distribute to different machines. Every zone, which is a circle or an outlined region in this picture, is managed by one or more name servers. So now, here's what I want to really move on to. The DNS protocol and DNS resolution. So the DNS, as well as being a system, the DNS is the name of a protocol that lets any host on the internet resolve or map a host name, which in our terminology is a domain in the hierarchical namespace, to its IP address. The way that it's going to work is, well, you can probably imagine it, and we'll see an example in just a minute, but I just would say now, if a host doesn't know anything about what the IP address of this host name is, it can always start at the root, at dot in the namespace. If it goes to that zone, it can then work its way down following the forward pointers to delegated zones until it gets to the zone that has the right host record in, and it will there find the IP address. So let's see how this works, because it probably sounds a little mysterious, but it works in pretty much the way you would imagine, going down from the root. So let's just imagine that we have a client here, or an originator of the request here, that should say flits.cs.vu.nl. What it wants to do is it wants to resolve robot.cs.washington.edu. That means it wants to find the IP address of this machine. Must be a popular machine, it's been turning up a lot in our examples, must have some great content, but to contact it we need that IP address. So what does Flits do? Well, I'm going to write over some of these steps. First step is that Flits will send a query to its local name server. That's this machine here. This is some machine that's just on the campus maybe, and it's serving all of the machines in the computer science department as their name server. It's going to help them with these translations. Now, if the local name server is just doing this at the beginning and it knows nothing about robot.cs.washington.edu, it will do what we suggested and go to the root with a query saying, hey, I want to find out the IP address of robot.cs.washington.edu. What can the root name server do? The root name server, well, is sending a reply here. The reply says edu. What that really means is the root name server is going to say, well, I don't know what the IP address of robot.cs.washington.edu is, but I can tell you who the name server is for .edu. And you can go and ask them. Please go away. So the local name server then knows who to contact for .edu, so it tries its luck and asks .edu, what's the IP address of robot.cs.washington.edu? Well, .edu, again, it doesn't know the answer, but it's a little more helpful. It can at least provide a pointer to washington.edu, who you ask. Washington.edu is going to say, well, you know, I don't know, but here's a pointer to cs.washington.edu. And finally, when you ask cs.washington.edu, what is the IP address of robot.cs.washington.edu, this name server can answer it because that domain is within its zone. It has not been delegated. It will send back the IP address. And the IP address will then be at the local name server who now has the answer, and it will send it back. In the last step to Flits, it'll say, well, here's the IP address. Wow, so that's an example of all of the steps that could be involved in translating that name. Well, let's talk about that example a little bit and see what was going on. One thing that I would like you to notice is that there were two kinds of queries that were performed in that example. The first was a recursive query. Here, Flits, for instance, asked the local name server what the resolution was, and the local name server then recursively performed all of the steps to get the complete answer and replied to Flits with the complete answer, rather than any of these little steps. This is called a recursive query. The other query were the other steps. These were the iterative queries. Here, when someone asked a name server in an iterative query, if the name server didn't know, it didn't then carry on further further queries to find out the answer and return it. Instead, it just immediately returned the best answer it had, the pointer to the delegated subdomain, and called it quits. It was not involved in the query resolution anymore. This is an iterative query. And you can see that we needed several iterative queries to be able to come up with the answer to a recursive query. So the iterative queries were where the local name server was making queries to all of the other name servers individually. I'd like you to think for a minute about just the differences between the recursive and iterative queries. Why should we have both? Why shouldn't we always make queries iterative or always make queries recursive? That's a good thing for you to think about in terms of the design of networks. So think for a moment, and I'll tell you the answer. Okay, you ready? So here's the answer. So there are advantages to both, of course. That's why we're going to have both. What are they? Well, the advantage of a recursive query is that it lets one party offload administration and work for another party. So the recursive query here lets the local name server offload a burden from the client so that it can be this is sort of like an IT practice, and similar to the way routing was not done by hosts, it was done by routers. We can move the smarts to this local name server, have IT people who know what they're doing administer it so it can work very well and use it as a point of management, then have very little going on in the clients. They will then only need a very simple query interface to communicate with the local name server. And there's less work on the clients. It also potentially can provide better performance because the server can cache resolutions across a pool of clients. So maybe if some other client next to you has been asking for a host name of something that you were interested in, when you ask for it, your local name server already has a resolution it can use. So there are a few benefits here. Okay, that's good. Well, why then would we bother with iterative queries? Well, the advantage of an iterative query is that it lets whoever is receiving it deal with it and look up the answer, send it back, and then forget about the query. No extra information or timers or anything needs to be maintained for a longer interaction. So it's very lightweight on the receiving end, an iterative query. This makes it easy to build some of the high-load servers. If you think about the root server or the .edu server, for instance, these servers can be receiving a very high load of queries because there can be very many clients all over the internet which are using these servers. So we would like to reduce what these servers have to do to handle a query so that they can scale more effectively. With an iterative query, the root's not doing any more than the minimum amount of work for you. It's pushing the work back to the local name server. So between both of these techniques, we're locating the bulk of the work on the local name server. I'll also talk about caching. So the resolution I showed you so far was the full sequence resolution. So we know it can work, but it doesn't look very fast in that there might be a lot of round trips to machines all over the internet to be able to translate that name. If possible, we would like the latency of resolutions to be as low as possible. Why? Well, because this latency directly adds, in some cases, to the page load time. Because before we can load a page on the web, we need to get the IP address of the server to contact. So if the DNS time is long, it can lead to lengthy page load times on the web. And of course, everyone wants the web to run quickly, so it works well. As well as there are other services too. So generally we would like this, other applications that depend on the DNS too. So we would like the DNS to run with as lower latency as possible. Now the obvious thing we can do here is cache. We can have the local name server remember past translations between host names and IP addresses. That way, when the same host or other hosts that are using the name server want to know the translations again, the name server can quickly return a cached copy. So for this to work, there are a couple of steps we take. First of all, responses that come from name servers carry a TTL or time to live field, which says how long information can be kept in a cache and used for. If the information is very stable, this time to live field might be long. If the domain is in flux or you need to go back and consult it, it might be kept quite short. It's fairly common for TTLs to be hours or a day, for instance. And in addition, caching in the DNS is interesting because we can cache partial answers that come from the iterative queries. So, for instance, when I resolved robot.cs.washington.edu, we learned information about a variety of servers, not just that IP address at the end, but we also learned the name servers for .edu, washington.edu, and cs.washington.edu. So all of that's information that can be cached and used for future queries. Let's see an example. Okay, so let's suppose that Flitz now wants to resolve the IP address of edu.washington.edu. Sorry, eng.washington.edu. Well, it's previously done some resolutions. They're going to help. So let's just imagine the steps. First of all, the client asks the local name server here, I would like the IP address of eng.washington.edu. What does the local name server do? If it didn't know anything, it would go to the root. The root would tell it edu, and then it would go to edu, and edu would tell it washington.edu, and so forth. But we've already done that on the way to get to through cs.washington.edu. So the local name server can shortcut this process because it already knows the name server for washington.edu. Therefore, assuming this information is still valid in the cache, so it's being looked up within the recent hours or a day or something, but if it's valid in the local cache, the local name server can send the query to the UW name server for washington.edu, and in this case, eng.washington.edu was in that zone, so it can be answered by that name server, who will return the IP address to the local name server, who can then convey it. And you can see here, we've cut out a lot of steps. So we've potentially made the resolution much faster. Okay, so that's caching. Caching is really quite important for improving performance of the DNS. I want to talk just a little bit about some of the name servers at either end of this process, the local name servers, new clients, and the root name servers at the top of the tree. So the local name servers, we said that a client contacts a local name server. So that means a local name server is typically run by your organization, by IT people in your organization, in your enterprise, or it could be provided as part of your ISP service. Now, this all depends on how your computer is set up. You could be running a local name server on your Linux host, say, or your host right now. Or your access point at home might also be running a local name server, which is then talking to your AP. This would maybe provide advantages by caching information for machines inside your house, which is available locally and quickly inside your house. It's also possible to use alternative systems for your local name server. Google, for instance, runs a public DNS, and you can configure your machine to use Google as a local name server. And you can look up on the web and read about it. Google suggests there are several advantages of doing this. They're trying to make the web faster. If you're interested, just Google them. That way you can play around with it and see how some of the name servers work. One point for us, though, as part of this system, if we're designing it, is that clients need some way to contact their local name server. So how are they going to know how to contact their local name server? Well, you can see I've already provided the answer for you here on the screen. I should stop doing that. But what happens is that the name server is something which is typically configured as part of DHCP. So when your host is assigned its address and other parameters, those other parameters usually include the IP address, maybe name, of the local name server so that you can contact it and use it. Okay, what about the other end, the root name servers? Well, they're fun too. As you can imagine, the root name server, that's dot, the very top of the tree, is pretty important for the DNS. I mean, if the root was taken down, we wouldn't be able to perform name resolutions. Well, not to worry. The root is served by 13 server names. They're called, so you can see it's not just one machine. It's replicated. There are at least 13 logical names there. They're called a.rootservers.net through m.rootservers.net. Now, this is important because every host, every name server, every local name server that wants to be able to answer queries needs to have information about the route, what their name is and what their IP address is, so they can contact the route and begin this resolution process. That's handled by using a configuration file. So it's just part of the configuration of local name services to provide them a file. It's by convention, it's called name.ca. The CA stands for cache. So if you like, it's the cold information you put in your cache at the beginning of time to bootstrap it and get it going. Now it's also the case that even though there are only 13 root server names, there are around 250 root server instances that are distributed around the globe. These machines together provide a highly reliable and reachable service for the whole internet because they're crucial for internet service. There's a very interesting trick here. You can read about it in section 529 of your text, Anycast. I'm not going to go into it in much more detail here because we just don't have time, but it's quite interesting. Many of these 250 server instances are reached by what's called IP Anycast. This is essentially a trick, a very clever trick, where multiple different physical locations around the internet advertise the same IP address. If you just assign them all the same IP address, what's going to happen? Will the internet break? Well, no, actually. What routing will do is it will take you to the closest place that IP address can be reached. So it will effectively route you to the closest replica of that IP address. This is called Anycast. And we're getting a bit of a performance gain by going to the closest one, as well as getting replication, which is good for reliability. And I'll just point out that these servers are reachable via IPv4 as well as IPv6, of course, so that the IPv6 internet will work. Okay, well, let's get have a little more fun with these root servers. I've just told you there are lots of them, A through m.rootservers.net. This map, taken from the rootservers.org website, gives you a snapshot of just how the root servers were deployed quite recently. So you can see that they're spread all around the world and there are all of these different servers. So it's really quite an amazing infrastructure that's been built up. Now, as we wrap up all of the resolution, I'd like to go through the DNS protocol a bit. We've seen pictures where all of the queries and responses are sent, the messages are sent, but we haven't really talked about them in much detail. So now I'll just tell you a little bit about the protocol. So it's a query response system. That's the queries and the responses we saw in the previous pictures. This protocol is built on top of UDP. Typically, it uses port 53. These messages need to be reliable, and we just have UDP, which is unreliable. So the implementation of the DNS implements ARQ, automatic repeat request, for reliability. So you can see here is a client sends a message. That's the request or the query, and back later comes the response. Everything worked here, nothing was lost. If something was lost, the client, using its ARQ, would eventually time out and retransmit. This means that the server is stateless. The server just gets these queries in and processes them. It doesn't need to run any timers to see whether someone's got a message or not. If this response didn't get through for some reason, it's like the ACK, then the client will send the question again. So this is very handy for building high-performance servers, that they can process a message, then forget all state about it. At the client, however, we need some way to link together a query and a response, so you know which ones are paired. This is done by placing a 16-bit identification number on the messages. So you can see here both the query and the response in this example happen to have an identification value of 1, 2, 3, 4. Okay. What else? Service reliability. So I showed you how the query response between a single client and a single server. The DNS is a system that should be reliable, and we provide reliability by using replicas. Here are shown that there are 3 replicas, A, B, and C, for a given domain. A client here can contact any of the replicas with a query and get a response. All of these replicas contain exactly the same information. What that means, and of course when they return information, they return lists of translations or resolutions, including lists of all of the name servers for the domain. So when B provides replies there, or when someone's told you about the domain, they've told you that all A, B, and C are name servers for that domain. That means that if B goes down for any reason, it's unplugged, it's blown up, whatever, then a client here can simply contact A instead, say, for a query and get a response. So clients will choose different name servers to contact, and they'll typically rotate their choices, or the servers will rotate information that they send out. This also helps to distribute the load, as well as providing reliability. So that's a nice feature of the DNS protocol. And finally, let me just say, one topic that is kind of notorious sticks out in that I haven't mentioned it yet, is security. Security is a major issue for the DNS. That's because if the DNS is compromised, then you'll end up contacting the wrong computer to get information. Imagine, for instance, you're trying to log into your bank and you're contacting the wrong computer. This is not good. Security was not considered as part of the original protocols, but as the internet grew and many parties began to exploit it in different ways, security has become more and more important. Nowadays, DNSSEC, or the DNS security extensions, are rapidly being deployed and used. They've been under development for a long time, and now they are partially deployed and their use is really beginning to take off. I just mention it now because it's an important part of the DNS system, but it's a topic that we're not going to look at until later. When we get to security, later on we'll look at this and other topics. So that's DNS resolution.